Hello and welcome to another Control Systems tutorial with me, Richard Pates. Today we'll learn about two concepts. The first concept is that of reachability and the second is that of controllability. Reachability is a concept that applies to individual points in the state space of a state space model. Roughly speaking, a point is said to be reachable if we can design a control input to drive the state of our state space model to that point. In contrast, controllability is a property of the state space model itself. A state space model is said to be controllable if every single point within its state space is reachable. Today we'll dive into these concepts in considerably more detail, and we will learn how to test for them when studying linear systems. In particular, we will develop linear algebraic tools to test whether a given point is reachable and whether a state space model is controllable. But why on earth would we want to understand these things? Well, control theory, as the name suggests, is all about trying to understand how to interact with systems so that they succumb to our will. Take, for example, the double pendulum illustrated on the left here. The double pendulum consists of three moving parts. This pendulum and this pendulum, which are connected together through this rotating joint, and the cart at the top, which is both free to slide from side to side and is also connected to the pendulum through this rotating joint. If we just release the pendulum from the starting configuration on the left, it would start to oscillate from side to side in quite an unpredictable way, and maybe eventually it would reach the downward configuration illustrated on the right, but nobody's got time for that. How, by interacting with the system, could we make this happen faster? Now, in the pendulum case here, we could just grab it, I suppose, with our hands and force it into the downward configuration, but suppose instead that we're only allowed to interact with the pendulum through the cart. We're free to control the position of the cart, but that's it. By moving the cart around in a clever way, are we able to drive the pendulum into the downward configuration faster? And that really is what reachability and controllability are all about. Suppose that we're given a state space model of our system of the form x dot is equal to ax plus bu. Can we work out how to design our control input u to drive the state x of our system from one point in the state space to another? And so we arrive at the definition of our first concept, that of reachability. A point xp in the state space is said to be reachable if we can find a control input u that will drive our system from the origin to that point xp in the state space in finite time. A helpful way to visualize what's going on here is to imagine that we have a set of axes describing our state space. I've illustrated it here, assuming that we have two states, x1 and x2. Points on these axes then correspond to different points in the state space. For example, the origin is described by the point 0, 0. The point xp, for which we want to determine whether it's reachable or not, will also have a set of coordinates, which I've just illustrated here. Applying different inputs then has the effect of pushing points around our state space. Suppose, for example, our system was initially at the origin here. Applying one input over one time interval might have the effect of pushing that point through our state space like this. Applying another input over perhaps another interval of time might push it along a trajectory like this. The question of reachability then asks, can we find some input over some time interval that will drive our system along a trajectory that finishes at the point xp? A natural question to ask is it possible to have points in the state space that are unreachable? To see that the answer is yes, let's consider another pendulum-based system, the dual pendulum. Like the double pendulum, the dual pendulum also consists of two pendula and a cart. However, this time both pendula are connected to the cart through a single point. We can now ask the question, is the configuration on the right, which corresponds to a particular point in the dual pendulum state space, reachable or not? We now see that if the only way to interact with the dual pendulum is through moving the cart from side to side, the answer is no. The origin for this particular system corresponds to the case where both pendula are pointing straight down and are stationary, and the cart is in the middle and also stationary. We now see that no matter how we move the cart from side to side, we cannot split the two pendula apart. This means that we can never arrive in the desired configuration on the right, and consequently, this particular point in the state space is not reachable. But how do we check whether a given point in the state space is reachable or not in general? Fortunately, there's a very simple way based on solving a particular linear system of equations. To construct this linear system, we need to build what is known as the controllability matrix, and to do this, we need to know our state space model x dot is equal to ax plus bu. In general, A and B are matrices, and the important feature here is that A is an n by n matrix. We then proceed to build a sequence of matrix products. Starting with B, we then construct AB, followed by A squared B, and we keep on doing this until we arrive at A to the n minus 1 times B, where n is determined by the dimension of A. We then take the elements in this sequence and slot them into a big matrix M as shown here. A point xp in our state space is reachable if we can solve the linear system of equations mv is equal to xp for v. To illustrate this, let's just do a few examples. So let's suppose that our state space model is described by this set of A and B matrices, and suppose we're interested in determining whether the point with coordinates 1, minus 1 in our state space is reachable or not. So on the previous slide, we saw to do this, we need to construct the controllability matrix, and to construct the controllability matrix, we need to build the sequence B, followed by AB, and so on until we get to A to the n minus 1B. Now, in our case, the A matrix is 2 by 2, which means that n is equal to 2, which means that we just need to construct these terms. So let's do that. Well, the first one is very easy. We can just copy it from up here. So the first entry in our sequence is 1 minus 1. And to form the next one, we need to form the matrix product AB. So let's do that. Writing out A, 1, 3, 4, 2, multiplied by B, which is 1 minus 1. And doing this matrix product to get the first entry, well, that's 1 times 1 plus 3 times minus 1, which sounds like it's minus 2. And to get the second entry, 4 times 1 plus 2 times minus 1 is equal to 2. So these are the two entries in our sequence, and to build our controllability matrix, all we have to do is slot them into the right positions. So let's do that. This means that our controllability matrix M is given by 1 minus 1, that's the first entry in our sequence, followed by minus 2, 2, that's the second entry. Now, we also saw that in order to determine whether the point xp is reachable, we need to see if we can solve the system of equations mv is equal to xp for v. So this is m, this is xp, let's just mark that m, and everything is 2 by 2 here, so that means that v has two entries, v1, v2, like so. And the question is, can we solve this system of equations for v? So just remember these matrices here. Right, so let's just quickly write that out again. So what did we have? That was our controllability matrix multiplied by v1, v2. And the question is, can we make this equal xp, which is 1 minus 1? Now, this is just the compact matrix notation for a set of simultaneous equations. And because the matrix here is 2 by 2, we have a set of two simultaneous equations. So let's just write those out. So the first line of this matrix equation reads 1 times v1 minus 2 times v2 is equal to 1. So v1 minus 2v2 is equal to 1. And the second line reads minus v1 plus 2v2 is equal to minus 1. And the question is, can we solve this system? Well, yes, we can. And in fact, we can even spot the solution straight away. We just say v1 is equal to 1 and v2 is equal to 0. And now, if we just check that quickly, the first equation reads 1 minus 0 is equal to 1. And the second, minus 1 plus 0 is equal to minus 1. So we have a solution, and therefore the point xp is reachable. Right, well, the eagle-eyed viewer amongst you might not have been too satisfied with my sneaky solving of the simultaneous equations last time, so let's try a very similar example where we keep the same state space model, but change the point that we're testing. So let's keep the A and B matrices the same, but let's ask whether the point with coordinate 0, 1, let's ask whether this point is reachable or not. So because the A and B matrices are the same, it means the controllability matrix will be the same. So when we try and solve the system mv is equal to xp, the left-hand side will be exactly the same as last time. So that means that when we convert this into a set of simultaneous equations, the only thing that will change is the stuff on the right-hand side. So the first simultaneous equation from before, that was v1 minus 2v2, that's the same left-hand side, and this time this will be equal to 0. That's the first of our xp coordinates. And our second simultaneous equation was minus v1 plus 2v2 is equal to 1 this time. So the point xp with coordinates 0, 1, this point will be reachable if we can solve this set of simultaneous equations for v1 and v2. So let's try and do that. Right, well, trying to spot solutions, it looks a bit harder than last time. So let's try and solve things a little more systematically. So let's eliminate a variable. Let's use the first equation to eliminate v1. That looks like a good equation to eliminate v1 with, because if we just rearrange it slightly, we see that it reads v1 is equal to 2v2. And to eliminate v1, let's substitute that into the second equation. So doing that, we get minus 2v2 plus 2v2 is equal to 1. And now we simplify that and we get 0 is equal to 1. which is a contradiction. And what that means is that this system of simultaneous equations has no solution, and therefore the point xp is not reachable. So now we've dealt with reachability, it's time for our second concept of the day, that of controllability. Reachability was a property of individual points within the state space. In contrast, controllability is a property of the state space model itself. In particular, a state space model is said to be controllable if every single point in the state space is reachable. So what does that mean? Well, if we draw out a set of axes, like we did before, to represent our state space, well, in order for the system to be controllable, this point would have to be reachable, and this point would have to be reachable, and this point would have to be reachable, and this one, and all of the points would have to be reachable. So how on earth are we supposed to work out if our system is controllable or not? Clearly, then, we're going to have to get a little bit smarter. We can't very well take each individual point in the state space and solve a simultaneous equation for each one. There are far too many points to consider. Instead, what we need is a deeper understanding of what it means to solve a set of simultaneous equations. The key insight that we need is that matrix multiplication can be interpreted as the addition of vectors. The equation that we need is given here. To understand what this tells us, we need to associate every column of the matrix M with a vector. If M has, say, p columns, these would be M1 through MP as illustrated here. Forming this matrix product is then equivalent to forming a weighted sum of these vectors, where the weights are given by the numbers v1 through vp. The reason this is useful is that it gives us a geometrical interpretation of matrix multiplication. In particular, it is the direction of these vectors m1 through mp that will determine whether we're able to solve the system of equations mv is equal to xp for general values of xp. The easiest way to understand this is to just do an example, so let's do that. To keep things simple, let's use the same state space model from before, which was given by these A and B matrices here. From our analysis earlier, we saw that the point with coordinate 1, -1 was reachable. However, the point with coordinate 0, 1 was not. This, in fact, already tells us that this state space model is not controllable, since we cannot reach this point here. However, let's try to reinterpret this result with our new understanding of matrix multiplication. Since the A and B matrices are the same, the controllability matrix will also be the same. When we computed this earlier, we found that it was given by the matrix with entries 1, -1, -2, and 2. The state space model will then be controllable if we can solve the system of equations mv is equal to xp for every single point xp in our state space. To understand this, let's rewrite this matrix product as the sum of two vectors. On the previous slide, we saw to do this, we have to take each column of the matrix M and weight it by the corresponding entry in the vector v. So doing this, we get v1 multiplied by the first column, which is 1 -1. And to this, we add v2 multiplied by the second column, which is given by -2, 2. To be able to visualize what's going on, let's plot the vectors associated with the two columns on a set of axes. Starting with m1, that's the vector 1 -1. So that's this vector here. Now we see that the effect of choosing different values for v1 will just have the effect of rescaling this vector, if we choose positive values of v1, this will lead to points like so, and negative values like so. But no matter how we choose it, the point will always lie somewhere along this line. Now let's do the same thing for the second term. So taking m2, so that's the vector minus 2, 2, minus 2, 2. So that's this vector here. The effect of choosing different values of v2 has the effect of scaling this vector. And now we see the issue. Since the vectors associated with both columns are pointing along the same line, no matter how we choose v1 and v2, we can only obtain a point that lies somewhere along this line. This perfectly explains why the point with coordinate 1, minus 1 was reachable. Let's plot the point 1, minus 1 on the set of axes. And what we see is that it lies on this line. Therefore, we can find values of v1 and v2 such that mv will equal this particular value of xp. It also explains why the point with coordinate 0, 1 was not reachable. The point with coordinate 0, 1, that's 0, 1, is here. This point does not lie on the line, and therefore there are no values of v1 and v2 which will cause us to reach this point. And here we arrive at our insight about controllability. As long as the columns of the matrix M can span the whole of the underlying space, we'll be able to solve mv is equal to xp. If they do not, we'll only be able to reach certain values in the state space. To make sure that we've really understood what's going on here, let's do another example and consider the state space model with A and B matrices defined as shown here. And let's ask the question, for what values of alpha is this state space model controllable? Now, to get started, we have to compute the controllability matrix. And to do that, we need to find the sequence B, AB, and so on. Since A is only 2 by 2, these are the only two terms that we need to find. So the first term, as before, is extremely easy. B is just 1 minus 1. And to get the second term, we need to form the matrix product AB. So let's just do that. A is 1, 4, 3 alpha. And we need to multiply this by B. And if we evaluate this matrix product, we get 1 minus 3, which still looks like minus 2, and 4 minus alpha. Ooh. So those are the two entries in the sequence, and to build the controllability matrix, all we have to do is slot these into the matrix as follows. In the first column, we put 1 minus 1, and in the second column, we put minus 2, 4 minus alpha. Now, this system will be controllable if we can solve the equation mv is equal to xp for every single point xp in the state space. And just like in the previous example, let's work out if we can do this by rewriting this matrix product as the sum of two vectors. So, like before, the two vectors we have to consider are v1 multiplied by the first column of the controllability matrix, 1 minus 1. And to this we add v2 multiplied by the second column, which is minus 2, 4 minus alpha. And we want to set all of this equal to our point in the state space xp. So to understand for which points xp we can solve the system of equations, let's once again plot the vectors that correspond to the columns of the controllability matrix. So let's plot this vector here and this vector here. So the first one is the vector 1 minus 1, which is exactly what we had before. So that is the first vector. And so by picking different values of v1, this first term can take on any value along this line, like so. Now the second term. So this vector is the vector minus 2, 4 minus alpha. So minus 2, 4, and then minus alpha. So let's just denote the distance alpha like that. And minus 2, 4 minus alpha. So that's that point there. And so we get a vector that looks something like that. And therefore, by picking different values of v2, we can achieve every single point along this line. And so what does this tell us? Well, it tells us that as long as these two arrows, so these two vectors that correspond to the columns of the controllability matrix, are not pointing along the same line, then by appropriately picking v1 and v2, we can construct any single value xp in the state space. And that's the answer to our question. As long as we pick alpha such that these two arrows do not align with each other, then the system will be controllable. So for what values of alpha is that true? Well, we can see from our picture that it's true for almost every single value of alpha. This corresponds to a line with slope minus 1 going through the origin. So as long as this vector here doesn't collapse onto this line, our system will be controllable. And so the system will be controllable for all alpha not equal to 2. In conclusion, today we learned about two main concepts, that of reachability and that of controllability. Reachability was a property of particular points in the state space of a state space model. A point was said to be reachable if we could construct a control input to drive the state from the origin to that point in finite time. In contrast, controllability was a property of the state space model itself. The model was said to be controllable if every single point in its state space was reachable. In order to test for reachability and controllability, we introduced the controllability matrix. If we assume that the matrix A is n by n, this matrix was constructed by building the sequence B, AB, A squared B, and so on, raising A to higher and higher powers until we arrived at A to the n minus 1b. We then built the matrix by taking the terms in this sequence and slotting them into the columns of the matrix as shown. We could use this matrix to test whether a point in the state space was reachable by seeing if we could solve the system of equations mv is equal to xp for the unknown v. Provided this was possible, the point xp was reachable. In order to work out whether every single point in the state space was reachable, we introduced an interpretation of matrix multiplication based on the columns of the matrix M. In particular, we showed that the matrix product MV could be rewritten as V1 multiplied by the first column of the matrix M plus V2 multiplied by M2, the second column of the matrix M, and so on. The directions that these vectors pointed in could then be used to determine which parts of the state space we could reach. This concept is commonly known as span. The set of all reachable points from a set of vectors is the span of those vectors. Provided this span was the entire of the state space, the model was controllable. In fancy language, this is equivalent to saying that the rank of the matrix is equal to n. And that's it thank you for your time, and I'll see you next time, where we will tackle the concepts of state feedback and pole placement.